Can you hear me and see my screen? Okay, thank you. So, as usual, let's mark your attendance before you do anything. So I hope you are done with that. So now let's continue on our week 8 material. First of all, we do a recap. So we are at the part whereby we go through the rules of differentiation so that we need not use the limit operation every time when we are given some elementary function to differentiate. So we have gone through the differentiation of the power functions, right? X to the power of n, for example. And we also gone through differentiation of the exponential function. So then we also looked at the product rule. So the product rule is for differentiating functions multiplied together. For example, f and g here, when they are multiplied together, then basically the whole idea is you just hold one of the functions and then differentiate the other. And then you just add up, then differentiating the function that you held just now, and then just multiply by the function that you differentiated beforehand here. Okay, so it's just like taking turns to differentiate each function and then summing them up altogether. So we also looked at the derivation of this product rule. All right, so we can also extend the product rule for functions or rather 3 or more functions multiplied together, and then we actually kind of like derive them here. So you can see that if you have f times g times k, for example, and that represents your function h, right? So 3 functions f, g, k multiplied together. So you can just apply the chain rule for any 2 functions, right, in a sequential order. So you can see that I actually apply the chain rule to g times k first, as you can see from here, right? Or rather, I applied the chain rule, product rule to f times g times k. So which means that you treat g times k as one function. Okay, so that's what happened. And then subsequently, you apply the chain rule again to this g times k. You can see differentiating g times k, right? Will ask to apply the product rule again. So it's actually product rule once and then product rule twice. Okay, and then you get this expression here, which represents the summation of these 3 functions multiplied together, whereby each function is taking the one function and then differentiating it. Okay, so you can see the first one I differentiate k, and then second one I differentiate g, and then the third one differentiate f. Okay, so it's like taking turns to differentiate each function and then summing them together. So that's the product rule. And of course, you can extend to 4, 5, or more functions multiplied together in the same analogous fashion. So we looked at some examples demonstrating the product rule. And then also ended, I think, the last lesson, right, with the quotient rule. Okay, so the quotient rule has more constraint in the sense that because product rule, you can choose to differentiate any of the function first. Okay, in the sense that you can choose whichever order that you prefer. However, for the quotient rule, you can't do that. Okay, so for the quotient rule, you have to strictly hold the denominator first. All right, and then differentiate the numerator. Okay, so you can see numerator is f and then denominator is g. So then you just minus, hold the numerator, multiply by differential of the denominator, and it's always divided by the denominator square, right? So this is a strict sequence to follow, okay, for the quotient rule. And then we also kind of like derive this quotient rule here. It looks like a mess, but it's really quite straightforward, just that you have to move terms around and then put the terms in a nice fashion so that you can get your quotient rule. So of course, I also mentioned that you can choose to use the quotient rule or product rule, okay? Because eventually the quotient rule is practically f times 1 over g, right? Because the differentiation of two functions, for example, u, v here, right? Of course, you can choose to view it as a product, right? U times 1 over v, okay? So therefore, if you apply the chain rule, sorry, not chain rule, product rule, all right, on this function. So the two functions are actually u of x, for example, multiplied by 1 over v of x. Okay, so effectively this can be viewed as u multiplied by, for example, some w, where w, right, is actually 1 over v. Okay, because v is a function of x, therefore w will be a function of x. So therefore, you can apply the product rule on u times w, right, instead of using the quotient rule u over v. Okay, of course, those will give you the same result. Okay, they will give you the same result if you differentiate them this way. So we also kind of like demonstrated this, right, by looking at the differentiation of this number 3 here. Okay, so initially we use quotient rule and then we got a result here. Then subsequently we use product rule and then we got the same exact result. Okay, so therefore this shows that regardless of what rule you use, as long as it is mathematically consistent with the principles, right, or with the first principles, you can actually obtain your answer. Okay, that's the beauty of mathematics. So today we are going to continue with the derivatives of trigo functions. So once again, of course, we are going to derive the differentiation of sine and cosine. I think I'll just do for one of them, then you can apply the same concept to the other. And then also look at some of the examples of how we apply. So let me just... hold on. So the recap here is that you have gone through trigonometric functions. Okay, so what is the sine of x? So as I mentioned before, sine of x is simply the vertical projection, taking that x is a angle. Okay, so let's say if you have a right angle triangle here, and this happens to be my x. So therefore, right, this guy is actually 1, the hypotenuse of length 1. So hence, this side, right, must be 1 times sine x. Okay, so this side must be 1 times cosine x. So I keep saying this for many times. And that is right, sine x and cosine x are just projections onto the y-axis or the vertical and the x-axis or the horizontal respectively. Okay, so sine x vertical projection, cosine x horizontal projection. Okay, of what? Of a hypotenuse or radius, if you like. Okay, so you can treat this in the Cartesian plane, right? Then this is can be viewed as a radius. Okay, emanating from the origin there. So therefore, this represents your trigo function, which is kind of like a sinusoidal and periodic function. So now we are going to try and derive the differential of sine x. Okay, so I believe some of you recognize that when you differentiate sine x, right, you get cosine x. You differentiate cosine x, you get minus sine x. Okay, so that's what you memorize when your secondary school or your poly teacher teach you. Okay, but today, right, because we have learned the concept of taking limits already, so we are going to apply that and derive why is it that the differentiation of sine is cosine, differentiation of cosine is minus sine. So those are the recap of the graphs. Okay, so it's quite a kind of like a handful here, right? But I'm just going to show you the trick. So as you can see, let's say my f prime x, let's say my f of x, right, is actually sine x. Okay, so it's not stated here, but let me just write it down. So let's say we have f of x is equivalent to sine x. So now, to find f prime, so we just use the limit operation. This is the standard definition of differentiation or finding the slope of tangent. So hence, right, we substitute x plus h into our sine function minus sine x over h. Okay, so this part will require some treatment. Okay, so what we do, right, is that we use the compound angle formula, right? Because or else, right, this function we can't do much with it, right? So we are like kind of like stuck. Okay, so we need to use some trigo identity. So I'm going to use the compound, also known as the composite angle formula. So certainly I don't remember what is compound angle formula, so I'm just going to Google. So just type compound angle formula. And maybe I take this one. Yeah, this looks pretty nice. Okay, maybe I take this one. So therefore, as you can see, I'm trying to differentiate sine, right? So I have sine x plus h, okay? Sine x plus h. So therefore, sorry, sine x minus h. Sorry, is it x plus h or x minus h? Oh yeah, it's x plus h. Okay, so therefore, for x plus h, right, I need the first guy, okay? So therefore, I'm just going to copy and paste this guy. That's the one. So you can see this is sine A plus B, right? Will give us sine A cosine B plus cosine A sine B. All right. So I'm going to use this identity. So which means, right, this x is my A, h is my B. You see that? So therefore, if you follow this, right, this is actually sine x multiplied by cosine h, as you can see here. Sine x plus cosine h plus cosine x sine h. Okay, so which means that all I need to do, right, is to treat this as x and treat this as h. Okay, of course this is plus, right? So whichever you treat as h or x, right, does not matter. Okay, of course if you swap x and h here, right, then you will just swap the terms here. Okay, so it wouldn't matter. So therefore, you can see that this, using the compound angle formula, will give us this expression here. Okay, then minus sine x will just remain as it is. Okay, there's no big deal with that. So now we can actually regroup the terms. So you can see this is sine x and this is also sine x. So we just group the sine x terms together. All right, and then we are left with this plus cosine x sine h, right? Okay, and then subsequently we just factorize out this sine x for the first term, right? Factorizing out. So hence we get cosine h minus 1 over h here. Okay, so at this juncture, for this first term, right, when we want to take the limit, of course we know that this sine x has no influence, or rather h going to 0 has no influence over this sine x term. Okay, so sine x term behaves like a constant in this limit operation. So we just ignore it. In fact, we can just factorize this sine x out of the limit operation if you like. So hence, we apply this limit h go to 0 into this expression. But this expression we have seen before, if you recall. Okay, so we're going to use the squeeze theorem. The squeeze theorem. If you still remember, right, when your h angle, the angle h is small because cosine h, right, is like cosine of an angle. Okay, so when your h angle is small, cosine h goes to cosine 0, right? Because h is small, right? So hence cosine h is actually 1, right? Cosine h, right? This guy is actually 1. So therefore you get 1 minus 1 over h, 1 minus 1 over h. So hence you get 0 here. You see that? Okay, so the limit of this guy, right, is actually giving us a 0. Okay, so using the squeeze theorem, let me use a different color for this so that I don't mess up with the first part. So this guy, right, is actually going to the limit h go to 0, 1 minus 1 over h. So therefore, this is actually equivalent to 0. Okay, as given here, right, using the squeeze theorem. Subsequently, what about the second term here? So we apply the same concept to our second term. Okay, so you can see that we have sine h over h. So once again, we have seen this before, sine h over h, right? So we use the squeeze theorem again. Why? Because when h is small, very close to 0, right? You still recall that this sine h will go to h, okay? Small angle approximation, right? Sine theta approaches theta when your theta is small, when you have very small angle. Okay, you still remember the comparison, right, of our vertical projection sine theta as well as the arc length, right? The arc length. So therefore, this guy, right, will go to h. So therefore, this guy actually gives the limit of h go to 0, h over h. Okay, h over h. So therefore, this is a constant 1, right? So therefore, you just have 1. Okay, so this is clear that the first term will just multiply by 0 and then disappear. And we are left with only what? We are left with only cosine x times 1. Okay, cosine x times 1. So hence the result is clear. You get cosine x. Questions? So in the process of evaluating the limit, right, this is a bit more, involved. We need to use the compound angle formula and then use squeeze theorem on each of our terms here. Okay? Or if you like, use small angle approximation to evaluate each of the terms. Questions on the concept? Sure, Kevin. So let me explain the last line, which is this part, right? So this part, we need to use squeeze theorem or small angle approximation to evaluate these two limits. Okay? So you can see that at this juncture, so at this second last line, right, they want to apply the limit to this entire function. So what they did is they applied the limit to each term. 4 terms here, 4 terms here. So therefore, this part, right, limit h go to 0 for sine x actually irrelevant, right? Because sine x, this is x, what? This is not h, what? So you let h go to 0, but sine x doesn't contain any h. So which means h has no influence on sine x. Okay, so we can practically, right, strike off. There's no need to even write this. Okay, and the same thing occurs here. Limit of cosine x, right? H go to 0. There's no h in cosine x here. So why do you even need this h go to 0? So you can practically just remove that. Okay, so now you have to evaluate these two limits here. So this is due to, we can evaluate this limit by using the small angle approximation or squeeze theorem, as they call it. Okay, so this cosine h, right, will go to what? Cosine h will go to 1 if you have h very small. Okay, why is that so? Because as we previously discussed, right? As we previously discussed, you can imagine that when you have very small angle, let's say this is my triangle. We try to draw a right angle triangle here. So you see, this is your h. And when this is very small, right? Where is the cosine h? Cosine h is this length, right? So this length is cosine h, right? So your hypotenuse is 1. So imagine when your h goes so small, don't you think that cosine h will go to 1? Okay, so rather when h is small, right, cosine x is approximated to 1. Okay, but you go towards 1. Then in the same fashion, this sine h, so this is sine h, right? 1 times sine h. So this sine h will go to what? This sine h will go to h. Okay, when this h is small. Why does it go to h? Because it approximates the arc length. So let me try to draw the arc length here. Okay, so you can see this is the arc length for my sector here, this sector here. Okay, so you can imagine when h is really small, you cannot differentiate the green line, right, the green arc from the vertical projection sine h. So therefore, we can say that this guy, right, actually sine h will now go to H. Okay, why does it go to H? Because S equals to R theta. You still remember? The arc length S, right, is equals to R theta, but theta is H, what? All right, but what is R? R is 1, what? Radius is 1. So therefore, you have 1 times H. Let me just put R theta. And this is 1 times H. Okay, so the arc length, right, actually approximates the vertical projection very well when you have small h. Okay, so we have gone through this part in the squeeze theorem before, but maybe it is clearer if you see the illustration here. Is that all right, Kevin? Okay, so you have cosine h go to 1, right? So you have 1 minus 1 over h, but 1 minus 1 is 0, what? Correct? So 0 is here. So therefore, sine h over h. So if sine h go to h, as you can see, sine h go to h when h is small, then you have h over h is 1. So this is 1. All right? So Kevin, I assume you are fine with that? Okay, good. So now, so therefore, right, we actually have sine x multiplied by 0 plus cosine x multiplied by 1, okay, after evaluating the limits right there. And then we have just cosine x, okay? And actually, we kind of like have a deduction of the differentiation of sine x is actually cosine x, right? If you still recall the last lesson, we actually tried to draw the differentiation, or rather the slope of sine x graph. Okay, because we just try to draw tangents, right? Then after that, when we draw tangents, then we see the tangent whether it's positive slope or negative slope. Okay, then after that, we just plot some points in the graph below, and then we draw the graph. Okay, and then we observe that the graph is actually very look very similar to a cosine x graph. Okay, so therefore that's the graphical so-called approach, which is of course just kind of like a sketch, or not exactly accurate, right? But however, we show that in this case, right, by using the limit operation, indeed mathematically, right, the differentiation of sine x is giving cosine x. Okay. So therefore, this is the thing here, right? Differentiation of sine x equals to cosine x. So next time we see sine of something, right, we just know that the differential is giving us cosine of that something. Okay? So there's something, this x may not be x, this can be a function of x here, right? So of course, we need to use other rules, including the chain rule, right, to differentiate that. Okay? But the basic of differential of sine x is cosine x. So therefore, you can just repeat this same operation, right, for the cosine x. Okay, but before we do that, let's look at this example, right? Differentiate x squared times sine x. So x squared times sine x is actually two functions of x multiplied together. Okay, because there's no way that you can combine that into one function, because it's not polynomial times polynomial. Okay, if it's polynomial times polynomial, you can just expand out the multiplication and then result in one so-called polynomial function. Then you can differentiate each polynomial term separately. Okay, but this case you can't. Okay, there's no way to simplify this expression. It's as simple as it gets, really. So therefore, recognize that this guy is f of x multiplied by g of x. Okay, so therefore you need to use product rule. So hence, what is my y prime? So my y prime of x, right, is just whole x squared. Doesn't matter which one you hold first. Then differentiate sine x. So just now we mentioned that the differential of sine x, right, is just cosine x. Plus, so differentiate x squared, get 2x, and then just whole sine x. Okay, so indeed, this is the product rule result, and you can simply maybe factorize out x, right? And you get x cosine x plus 2 sine x. Okay, so hence you use the product rule together with the trigo differential of sine x in the process. So using same methods, right, you can actually show that the differentiation of cosine x is minus sine x. Okay, so I'm not going to go through this. It's actually here. So you will need to use the compound angle formula, and in this case, right, you will need this guy, cosine x plus h. All right, and then you have this expression here. So you see the minus there. Okay, so the minus is the reason why you have differentiation of cosine is minus sine. Okay, it's minus sine, right, due to this negative term here. Okay, so I'll leave you to try that out on your own. So as you can see from here, we can also use limits, right, to differentiate tangent x. Okay, but however, when we use limits to differentiate tangent x, right, the compound angle formula for tangent x is a bit more tedious to use. Okay, because as you can see here, we still have our tangent x compound angle formula. Okay, but it comes in the form of a fraction, so it's a bit nasty to use. All right, but still can do lah. You need to, combine denominators and all that. So the process is a bit longer. Okay, but nevertheless, it is easier if you use the quotient rule, because after differentiating sine and cosine, right, we already know that differentiation of sine is cosine, differentiation of cosine is minus sine, right? So therefore, why not we use the quotient rule in the differentiation of tangent? Okay, because we know that tangent x is just defined as sine over cosine. So hence, using the quotient rule, as you can expect, right? So differentiation of sine over cosine, hold the denominator first. Differentiate sine, okay, the numerator, minus hold sine, the numerator, then differentiate the denominator. So, but now this is no big deal because we already know that differentiation of sine is going to give us cosine. Okay, and then similarly, differentiation of cosine is going to give me minus sine. So hence, what do I have? I have cosine x times cosine x, which is just giving me sine square x. Then minus sine x times minus sine x. So it's going to give me sine square x. So hence, I get 1 over the denominator, which is my cosine square. So I get 1 over cosine square, which gives secant square x. Okay, so for those who have done differentiation before, you know that differentiation of tangent x is secant square x. Okay, so this is the reason why, right? So hence we have the differentiation of the three functions already. Okay, sine, cosine, and tangent, right? Effectively, we can use the chain rule together with these three differentials, right, to get all the differentiations of secant x, tangent, cotangent x, cosecant x as well. Okay, but that will come in after we discuss the chain rule. Okay, so for now, sine, cosine, and tangent are obtained. All right. Okay. So you can expect here, we can use the chain rule. We can also use the quotient rule, right? So maybe we just do one which is as a practice. Okay. Maybe I just do one for cosecant. Okay. So for example, so if you try to differentiate cosecant x. So, but we know that cosecant x, right, is actually what? It's actually 1 over sine x, what? So this is 1 over sine. So 1 over sine, we can use the quotient rule. So quotient rule means, right, the numerator is 1, but the denominator is sine x. So we have to hold sine x first. Then I differentiate the numerator. But when I differentiate the numerator, it's actually 0. Okay, because differentiation of constant will give me 0. So minus, then subsequently I differentiate the sine x. So therefore I get cosine x. Then I hold the numerator, which is 1. Then divided by sine x squared, or sine square x. So hence, right, the first term disappears. So what do I have? I have minus of cosine x over sine square x. Okay, if I like, right, I can actually rewrite this in terms of the basic trigo functions. And that is, this is actually minus of 1 over sine x multiplied by cotangent x. Is that right? Okay, so if I want to go one step further, of course, I can write it as minus cosecant x tangent x or cotangent x. Is that all right? Okay, so this is actually the differentiation of cosecant x. So it gives cosecant x cotangent x. Let me put a bracket here for clarity. Questions? Okay, so you can do the same with secant x if you like, or cotangent x if you like. Okay, so basically I just showed you this guy. So you can try the other two yourself. So now we talk about the applications of trigonometric functions as well as their differentials. I think you have seen this in action before already. Trigonometric functions, right, are often used in modeling of real-world phenomena involving vibration waves as well as elastic motion, as well as some kind of reciprocatory motion. Okay, so as long as there's some periodic smooth motion, typically you can use trigo functions. All right, although the trigo function may not be, like friendly looking. For example, in your midterm, so let me just get your midterm out. So you can see here, for example, in your midterm, right? Let me just increase the size here. Okay, let me just download this. So if you look at the last question on the crank slider mechanism, okay, so I've actually mentioned that this guy actually is the basic mechanism for compressors as well as engines. Okay, so for an engine, right, this slider is actually your piston. Let me just capture this guy here and show you actually how the mechanism is being used. So if you look at this mechanism, right, for an engine, what they do is they actually have a cylinder here. Okay, they actually have a cylinder here. So this cylinder and this guy, this slider is a piston. So this is a cylinder. Of course, the gap is not so big, right? So what happens is that you have your spark plug and then you also have your fuel injection here. Okay, so you can expect, right, when the spark plug is activated at some periodic intervals, right, then what happens is that you have an explosion. Okay, so I think you know that when you have an explosion here, right, it's going to cause high pressure. So when the high pressure occurs, it's going to push down this piston or slider, right? And thereby when this guy pushes down, right, then this crank is going to rotate. Okay, so of course, if you time the spark plug in a so-called synchronous manner, you are going to get this crank, right, rotating continuously. Okay, so basically this is the mechanism for our internal combustion engine, okay, which is some super dated technology, right? And this guy, right, is also being used as a compressor mechanism, compressing mechanism. For example, the compressors, the refrigeration compressors, right, that you get in your refrigerators or in most refrigerators is making use of this mechanism. So what happens in the compressor is that, right, you actually have an electric motor. So now the prime mover is actually connected to the crank, okay? So which means that electric motor, right, is going to rotate the crank. So when this crank is being rotated, right, as you can expect, this slider or piston is going to pull out. Okay, when it pulls out, right, what happens? The gas is going to, refrigerant gas is going to go in, right? So when the gas goes in, right, it's going to get so-called refrigerant being sucked in at low pressure. Then subsequently, when this piston, right, is after the angle of pi here already, so it's going to rotate back. So then this slider is going to compress. You can imagine, right? When this thing is here, when your crank is actually at this position, right? This is going to be having maximum volume in this cylinder, okay? Then after that, right, your crank start to go back. So when your crank start to go back, right, this slider is going to start to push back. The slider is going to start to push back. This piston, when it pushes back, it compresses. So when you have compression, right, the pressure increases. Okay, so after the pressure increases, if it exceeds the discharge pressure of your refrigeration system, right, the hot gas or the hotter refrigerant, right, is going to go out. Okay, so therefore, this is the basic mechanism for a compressor as well as a engine. Okay, an engine. So therefore, what is the so-called big deal with this mechanism? Well, if we know what is this length, the length of OB, right, or Y as a function of theta here. So if you recall, right, we actually tried to, let me go back to the midterm exam. We actually tried to derive this expression. Oh, sorry. Let me see, where's my function? Yeah, this is the function. So we actually tried to derive this function. So you can expect that this function is what? It's a function of cosine theta and cosine something here, which involves sine theta as well. So eventually, right, you want to know what is the height of your piston, or rather position of your piston, right, pertaining to the crank angle, theta. So this is an example of trigo functions, right, being used in an actual mechanism widely applied in the real world. Okay, and this is important. Why is that so? Because if I know the position of my piston, I can actually know, right, what is the pressure in my mechanism. In this case, let's say, for example, if this is a compressor, right, I can actually know what is the pressure here. I want to know what is the pressure as a function of time. Okay, so if I know the pressure as a function of time, and guess what? I can actually take the pressure, multiply by this cross-sectional area, right? I will be able to get the force. So if I know the force, I'm able to integrate with respect to time. I can get the work done or energy consumption. So you can see the link. So the big picture, right, is to understand what is the power consumption, right? So that you can actually work out what is the efficiency, for example, of such a system. So therefore, or else, how are you going to obtain, for example, an efficient design, right, of an engine or a refrigeration system? Okay, so the same refrigeration system is also being used in your air conditioning system, Okay, so as you know, right, air conditioning system, they constitute up to 50% of any building. So if you want to go green, if you want to solve climate change, right, you have to design efficient systems which actually mainly point to those heating and refrigeration systems, right, that constitute a large percentage of the building's energy consumption. Okay, so therefore we want to know what is the efficiency, and therefore we want to know what is the power consumption, and therefore we want to know what is the pressure, and therefore we want to know what is the position of the piston. Okay, so you can see everything is linked together. All right. So I hope I just give you like a broad understanding of what is the mathematics used for. So therefore, we are going to come back down to our notes here and see how we can actually use the differentiation process, right, to analyze the velocity and acceleration of our simple trigo function for this vertical spring. So as you can see, we have an object at the end of a vertical spring that is stretched 4 cm beyond its rest position. Okay, so when the spring is unstretched, it's actually here. Okay, so it is about here, right? So which means that if you imagine, right, you have this same cube here. So there's no cube. So of course the spring is going to be unstretched. So therefore, right, this is the zero or equilibrium position. Okay, if you do not have a mass. But when you hang the mass, right, obviously this mass, or rather the weight, is going to stretch the spring here. So therefore it stretches down by 4. Okay, by 4 units. So therefore, the problem here is that when the spring is stretched beyond its rest position, hold on. Okay, my fault. So therefore, this is actually the equilibrium position with my mass. Okay, so this spring, right, is actually stretched already, it's pre-stretched. So this is the zero position, equilibrium position. So this position actually represents, right, summation F is equivalent to 0. Okay, with the mass, Okay, so if you think about it, right, this summation F equals to 0 in physics terms, right, is actually representing that you have a weight, okay, and that's the weight of whatever load that you hang on the spring, and you also have a spring force. So then you ask, what is the spring force? I think you might have gone through basic physics, right? And you know the spring force is given by Kx, okay, or in this case Ks. So the spring stretches by 4, okay, and depending on what is this spring constant K, right? This Ks force, right, the spring force will balance the weight here, okay, at this zero equilibrium position. Okay, so that's the idea here. So now, what happens is that we pull on this mass to 4 units down, and then we let go. Okay, so common sense or maybe experience tells me that when I do that, right, this mass is going to vibrate. Okay, so how is it going to vibrate? It's going to vibrate from this position. So if you let go, right, you hold here and you let go. So what's going to happen? The restoring force is going to push up the mass. Okay, so this mass, right, is going to push up, go to the zero position, but because of inertia, it's going to overshoot. So it's going to overshoot to what? To -4. Okay, hold on now, let me show a different color. It's going to overshoot to this -4 position and hit about this point. Okay, I can actually prove that using Newton's second law, right, summation F equals to ma on this mass here, we can actually prove that the mass is going to vibrate within 4 to -4, okay, in this range, right? But however, I'm not going to go through that here, okay, because it takes some amount of time to do the derivation. So therefore, the spring vibration, right, is going to be within -4 to 4, okay? So you can imagine this is what we call the travel of the spring mass system. Okay, so this mass, right, is going to go up, down, go down, and then, you know, continue this motion forever, right? Of course, that's assuming that if you do not have any damping or air resistance. Okay, so hence, because of this vibrational motion, we have this 4 cosine theta. Okay, and this 4 cosine theta must agree, right, with the vibrational motion here. And let me show you. Okay, so the logic here is, let's say we have time t, and this is our s of t. So it writes here s equals to f of t, okay? But effectively just s of t, doesn't matter. So now, we think about it. At time t equals to 0, right, you pull. So at t equals to 0, s equals to 4. So at this position, t equals to 0, s equals to 4. So s equals to 4 is where? S equals to 4 is here. Okay, some positive value. So now you let go. So what's going to happen? The spring force is going to pull back the mass. Okay, so when it pulls back the mass, right, it's going to return to the zero position. Okay, so therefore it's going to come down to zero position. But as I mentioned, because of inertia, this mass is going to overshoot. So overshoot to where? Overshoot to -4. Okay, so you can imagine when it has position at -4, eventually, right, gravity is going to pull it back down again. Okay, so when it pulls back down, it returns to the equilibrium position again. But because of inertia, it's going to overshoot again. So you can see the forces at play here. Okay, and this is going to be the trend, assuming that you do not have any air resistance or frictional so-called damping. All right. So hence, if you look at this expression, right, isn't this a cosine graph? Okay. So of course, I draw for t more than 0. Right. If you extend to t less than 0, right, which is maybe looking something like that. So you can see that it is indeed looking like a cosine graph. Okay. So hence, we can use 4 cosine t, right, to represent the vibrational motion of the spring mesh system here. Questions on this understanding? So this is the physics. I'm not sure if you guys are taking physics now. Can someone answer me? Are you guys taking physics now? Or have you taken physics before? Not taking this SEM. Then last SEM take already. Have taken before? No? So have not taken physics before. Oh, I see. Okay. Yeah. So for the students who have not taken physics before, you find this fuzzy, not so critical. Okay, because we are really trying to introduce the mathematics, right, associated with such physical phenomena in this course. Of course, if you have taken physics before, it helps you appreciate the application here. Okay, but if you have not, it's fine. Okay, because we mainly just deal with the mathematics. Okay, so in any case, later on when you take physics or some physics related topics, right, you have the mathematical background already, so it helps you understand the physics even better. Okay, so therefore let's come back to here. So having understood the concept of this function in its application to the spring mesh system, right, now we are supposed to find the velocity and acceleration at time t and use them to analyze the motion of the object. So therefore, really, because previously we have actually learned that the velocity function, right, is just the differentiation of the displacement function. Okay, so hence, right, velocity is actually v of t is actually ds dt. Okay, so just differentiate this 4 cosine t, right, as a function of t. So which is really no big deal. This 4 is a constant. So you just let it be, and then differentiate cosine t, right? So you get minus sine t. Okay, so differentiate s, you get v. So therefore, what is the velocity function? Minus 4 sine t. Okay, so you can expect that when t is 0, so this must agree with the motion that we expect. Okay, when t is 0, what's the velocity? Velocity is 0. Okay, and that makes sense. Why? The reason is because when you try to let go, what happens to the mass? When you try to let go at t equals to 0, right? The initial velocity of the mass is 0. At t equals to 0, v equals to 0. Okay, v is equals to 0 because v is minus 4 sine t, what? So sine 0 is 0, what? Correct? So therefore v is 0. So initial velocity is 0, all right? Because you let go. So therefore, when you let go, right, the spring force is going to cause acceleration back to the equilibrium position. So where is the velocity now? Velocity is upwards. So take note that your s, right, is actually positive downwards. So this s positive, right, downwards. So you can see when t equals to 0 or t more than 0, right, this velocity is going to be v at t more than 0, just after 0. Okay, so maybe I say t equals to 0 plus, right? When t equals to 0 plus, what's happening? This is going to be minus 4 sine 0 plus. But when you go sine of a very small angle or sine of a very small value, right, this thing is going to be positive. So if this is positive times minus 4, what do you have? A negative velocity. Does that make sense? Yes, it does, because once you let go, the velocity is going to bring the mass back up. You see that? Okay, so therefore, right, this negative direction is correct. Okay, opposing the positive convention that you assume for the displacement. Okay, so I hope you see the relationship, right, between the function here and the motion of the object. Okay, that's what I meant by physical meaning. Understand the physical meaning of your mathematical equations. So this is my velocity, right? So you can expect the velocity is going to be sinusoidal as well, as you can see this sine t here. Okay, because eventually, as you can expect, right, when this mass is passing its equilibrium position and then going back up, then eventually the mass is going to come back down, right? Okay, it's going to bounce back down. So when it bounces back down, the velocity is going to go positive. Okay, so that's why you have the sine function here, fluctuating between negative and positive values. Okay, so that's the velocity. So now, extending to the concept of acceleration. So acceleration is really just the differentiate or the differential of velocity. So dv dt. Okay, so since we have our velocity function here already, then there's no big deal. We just minus 4, right? And then this is cosine t. Okay, acceleration is minus 4 cosine t. So some of you may be wondering, why is it that acceleration is actually minus 4 times 1 when t equals to 0? Okay, because if you inspect this guy, minus 4 cosine t, what happens when you have at t equals to 0? At t equals to 0, s equals to 4, v equals to 0, but the acceleration is equals to minus 4. Okay, because it's minus 4 cosine 0. What? So just now we just mentioned that this guy is 4 cosine t, right? So minus 4 cosine 0. Cosine 0 is 1. What? So acceleration at t equals to 0 is minus 4. Minus 4. So is it correct or not? Is acceleration negative correct or not? Any guesses? I mean, by the maths, it has to be correct, but physically, what does it represent? Any takers? What does negative acceleration mean in this case? Deceleration. It's actually not deceleration at t equals to 0. Okay, but good try, right? It's actually deceleration in the positive direction. But in this case, it's better to understand it as acceleration in the negative direction. So you can imagine at t equals to 0, right? A equals to minus 4. So what happens to this block is that it's trying to accelerate back at t equals to 0. Okay? And this exactly corresponds to the understanding of summation f equals to ma. So of course the mass, right, is just of mass m. It's a constant. So you must think, when you have the mass displaced to this position, right, there is going to be a net force, right? The reason is because at this 0 position, the spring is already stretched already. Okay, it's already stretched for some distance. So therefore, if you stretch it more, what's going to happen? Let me draw this guy at this position. So therefore, this mass at this position is going to experience a larger spring force than the weight. So you can see that your weight, right? Let me just draw the weight here, running out of space. So this spring force at this position is equivalent to the weight. Okay, Ks is equal to weight. But however, when the mass is put down even further, right, you can expect, because the spring is displaced more, so therefore the upward force is more than the weight now. You see that? Okay, so therefore you get a larger spring force. So Ks minus the weight, right, is going to be net positive. All right, so when this is net positive on the left hand side, on the right hand side, it must be net positive as well. So m is a constant. So therefore this A must be positive. Okay, acceleration must be positive. So you can expect that, actually this is negative. Okay, because upwards minus down. So therefore up is negative. So this is negative, and therefore A must be negative. Okay, the spring force Ks, right, is bigger. So this is actually in the opposite direction. So therefore negative force. Okay, so hence you can see that the acceleration here is minus 4, making sense. All right, because of the larger negative force caused by the spring, okay, as compared to the weight. So I hope this is making sense to you of why the acceleration, right, is giving you -4 initially, okay? And then, of course, it's still going to vary in a sinusoidal fashion, right, given by the cosine t, because as expected, after some time, right, this mass is going to overshoot its zero position, okay? After it overshoots its zero position, right, it's going to get so-called pushed down by the spring. So now the acceleration becomes in the positive direction. Okay, so once again, the acceleration is also fluctuating between positive and negative values, hence giving us this cosine t function. Questions on this example? So of course the differentiation is trivial, okay, but there is a correlation to the motion, the actual motion of the mass. Okay, good. So whatever we have explained just now follows this graph here. Okay, so you can expect that when your S is starting at 4, okay, so this is what, 4 sine t, right? Still recall that this guy using, sorry, 4 cosine t. So S equals to 4 cos t. So you can see cosine function. Then subsequently we differentiated. So what is my V? So this V is equals to -4 sine t. So -4 sine t, you can see that this is sine function is like that. So minus, right, you just reflect on the t-axis. So therefore, -4 sine t. Then subsequently, your acceleration. So your acceleration here, right, is -4 cosine t. So -4 cosine t, as you can see, is cosine t, 4 cosine t, but reflected about the t-axis or horizontal axis. So therefore, you got negative cosine function. Okay, so therefore all three functions, right, are sinusoidal graphs. So let us complete this last example before we take a break. So I suppose to differentiate this function of trigo expression added together. So we just need to use our rules as per normal. So hence, right, f prime x is going to be, so this is just cosine x over 2, right, which is half cos x. So I can just differentiate cosine x directly. So hence I get minus sine x. Then apply the differentiation to the second term. So square root 5 is just constant. Then you just differentiate sine x. So square root 5 cosine x. Then plus, so what is this? This is actually x to the power of 7 over 3. So hence we can just differentiate as it is, bring down 7 over 3, and then x. Then the power 7 over 3 minus 1 is going to leave me 4 over 3. Okay, so hence this is my answer already. So hence I have minus sine x over 2 minus square root of 5 times cosine x plus 7 over 3. Then if I want, I can write it as, I think I just leave it as 4 over 3. Okay, because writing it as a fourth root is a bit weird. So this is the answer. Questions? So looks like you're fine. So let's take a break. So break till 12:10. Okay, so let's continue. We are done for this week's material. So I think what I can do now is, before I jump to week 9, differentiation rules 2, right? I think we probably can have some time to go through maybe the worksheets. Okay, so worksheet is something that you need not hand in, but it's just providing you with more practices. And usually the worksheet questions are somewhat a bit easier as compared to the homework, right? So we have completed week 8, so which means that next Friday you should be able to hand up your homework 6. Okay, I'll make an announcement in the MS Teams. So let's look at homeworks, worksheet 6. Okay, and go through maybe some of the questions for further practice. So we're supposed to, let's look at question 1. So given the graphs of f, right, assume the axes have equal scales, sketch the graphs of f prime below them. Okay, so as I mentioned before, for sketching of graphs, it is best to firstly sketch those points where you have 0 gradient, okay, which means that the tangent of those graphs, right, are 0. Okay, so therefore if you look at the first guy here, we can identify 3 points, right? So at this point, it's a 0 tangent. Let me just increase the thickness here. So we have 0 tangent here. So this is 0 tangent, which means that it is about this part. So this must cross the x-axis, okay? Because this guy is my f prime. So this is my f of x, and this guy is my f prime of x, okay? So therefore for f prime of x, I must have 0 here, okay? 0 gradient, 0. So therefore, the same goes with this point. So this guy, and the same goes with this point. Okay, so therefore I have 3 points whereby my graph, right, must actually cross the x-axis. Let me just make this a bit more symmetrical. So then subsequently what we do is this. We estimate the gradients by drawing tangent lines, right, and see how relatively steep they are, okay, as compared to other points. So you can expect that this is very steep, okay, so I'm just going to put like maybe 3 negative signs here, very steep in a negative slope, and then this is getting less negative steep. So this part, right, maybe 2, and then this part, right, getting less negative steep. Okay, so what you have here is on the left side of this 0 point, you can inspect that you're going to get negative values. Okay, so negative values is going to go up, right? It's going to go up. All right, so therefore it is possible that, of course, the exact profile of your f prime graph here, we will need the exact function of f of x. Okay, so therefore by visual inspection, right, you are not able to know how actually the graph goes from negative to the 0 point here. Okay, so just going to estimate. So hence, right, this guy maybe looks like, maybe something that looks like that. Okay, so once it go to the 0 point here, then we can expect that this is going to go positive. So it goes from slightly positive, maybe slightly positive, to maybe this part that is more positive. Okay, more positive. Then this part go back to slightly less positive again. So therefore, you can expect this guy is going to jump up to a maximum positive and then go back down to 0. Okay, so I will expect that this is maybe somewhere here, and we are going to get maybe something. Let me try to do this smoothly. Okay, something like that. Okay, so as you can expect, this is still positive. So the most positive is at this point, okay, at the so-called point of inflection here. Then after that, it goes less positive and go to 0. So it is logical that this thing will come back to 0. Okay, so I don't know how it comes back to 0. It could be like that. It could be like that. So dependent. So let's analyze further. So this part is going to go slight negative. Okay, so slight negative. And this is going to go more negative. And this is going to go slight negative again and go back to 0 again. Okay, so we can expect that this guy, right, is going to be maybe looking something like that. Okay, so of course I just extend to the positive side here. Okay, which is this part, right? You can see that this is going to be positive, very more positive, and this part is very positive. Okay, so it conforms to our graph here. All right, of course my graph is not so smooth, but I think you get the general trend there. Questions on how we sketch the f prime of the graph from F. Okay, so this is basically just relating the slope of the tangent line to the value, the function value of f prime in the graph here. Okay, so I'm going to leave Q6 to you for practice, and maybe let's look at Q10 here. So this Q10 here is somewhat interesting because there is actually a point of right, whereby your function is not smooth. Okay, so I think I mentioned this before, and that is right. In order for you to draw the tangent, your graph at that point must be smooth. If it's not smooth, then you cannot even draw a tangent. Okay, because that's what a tangent is, right? It has to be at a particular point, right, whereby the tangent is actually best approximating the line right at the point, okay, of the graph. So therefore, if you have a kink, there is no tangent graph there. Okay, so you can't draw a tangent there. So therefore, if you cannot draw a tangent there, right, which means that the f prime is not defined at this point. Okay, so therefore we can just write a note here. At x equals to 0, f prime at 0 does not exist. Okay, and this is because, right, you have a kink here. Is that right? Okay, so once you identify that, right, then we can actually start to sketch this. So this is pretty clear that it goes from negative to more negative, although the so-called change is not super obvious, but I think we can still agree that it goes from negative to maybe slightly more negative, and then this part, right, goes very negative. Okay, so therefore the function is actually going from here to here. Okay, so of course the trend, the exact trend of how the f prime looks like, right, depends on the exact function here. Okay, so I'm going to just assume that this is giving me the, this is actually giving me, I'm just going to assume a function here, which is actually f of x, right, is equivalent to the square root of mod x. Okay, square root of modulus x. It will look like that because if you substitute in any positive x, it will give you this graph. Okay, I'm just going to assume that this thing is actually going to 0 here. Okay, because yeah, I'm just going to assume that. So when x is negative, right, it will also give you square root positive. So it's going to give you this part of the graph. Okay, so you can verify the graph in decimals. So when you have that, right, actually your graph here, right, is going to look like that. So therefore, negative go to very negative. So you can expect that this guy is going to go this way. So negative, then go to very negative. Okay, so there's going to be an asymptote here. There's going to be an asymptote because this part, right, is actually infinity gradient. Okay, for my square root x graph. All right, and then this part, right, as you can expect, so this guy is going to go from very positive to less positive, and then to even less positive. Okay, of course that's my deduction here, right? It looks like a bit like, you know, this way. So hence this part, right, is going to go this way. Okay, of course this exact trend is only possible after I assume this square root modulus x graph. Okay, and we can actually somewhat prove it mathematically, because if you know your f prime is, if you know your f is actually square root modulus x, right, you can actually compute your f prime already. Okay, how do you do that? Well, it is quite clear. If your fx is this, then you can define it in a piecewise manner. Okay, so we know that it's going to actually give us, right, square root of x for x more than equal to 0. Okay, you can see if x is positive or 0, then effectively the modular sign wouldn't matter. Okay, because if your x is positive, right, is modulus positive, still positive. So you can just safely remove that modular sign. How about when your x is negative? So when x is negative, it has to give you square root negative x. So this is when x is negative. Why is that so? Because when your x is negative, the modulus make it positive. So therefore, what is happening? It takes the negative x and multiply by a negative 1. So you can see that. Okay, so if x is negative, negative times negative is always positive, right? And that is satisfying the modulus operation. Okay, so when you have something like that, right, of course we can do our f prime. Okay, so therefore from here we can have f prime x is equivalent to, so square root x, when you differentiate, right, I believe we have done this many times already. So this is really just giving me 1/2 square root x. Okay, and just we have to be careful in the sense that this is equal to 0, right? So we cannot include equal to 0. So x is only more than 0. Okay, for x more than 0. Then similarly, this is going to give me, so this is square root minus x. So in order to differentiate this guy, right, actually this is minus x to the power of half. Okay, minus x to the power of half. So therefore, it's going to give me minus x to the power of half, right? So I just throw the minus outside. Then I just differentiate x to the power of half as it is. So therefore, I have minus 1/2 square root x. Okay, and this is actually giving x less than 0. So notice that x equal to 0 has been removed. Okay, because at x equals to 0, we cannot define f prime. Okay, because of that kink over there. Is that all right? Any questions with the, yes? Yeah, if you want, you can just unmute yourself and talk if it's easier. Yeah. My fault. Obviously, the positive side is wrong, right? It's positive. How can it be like that? So it should be like that. Thanks, Guan Yu. Yeah, it should be like that. Wait, this is positive. It should be like that. Okay, my fault. It should, of course, it shouldn't be like that, right? Doesn't make sense. So it should be like that. Okay, thank you very much. Okay, so I think it conforms to the graph here, right? Thanks, Guan Yu. So conforms to the graph here. You see, this is minus 1/2 square root x, right? So you can see this negative value. So when x is, hey, hold on, be careful. Did I make a mistake here? Okay, this is definitely my mistake. This is square root minus x. So my mistake here. Okay, so let me differentiate this. My mistake here. So you can see this is differentiation. Okay, let me just do it here. Differentiation, right, of minus x to the power of minus x to the power of half. Okay, so just now I made the wrong assumption that I can just take out the minus here, but I cannot. Okay, because this power half, right, is actually for this minus x as well. Okay, for this minus x as well. So therefore, what I can do here, right, is I will have to use the chain rule. Okay, I have to use the chain rule. So I jumped the gun a bit, right, because I used this assumption of this expression here. Okay, so let me jump the gun a bit. We're going to touch chain rule maybe later on or next lesson. Okay, but let me just demonstrate that. So therefore, this is d dx of minus x to the power half, right? So I still bring down the half as usual, differentiate as per normal. Okay, bring down half. Then I have minus x. Then I put back minus x, right? And then just take this power half and minus 1. So therefore, I get minus half. Okay, so this part is exactly differentiating as per normal. okay, just like a power function, right? But then I need to use the chain rule, and that is right. I need to differentiate minus x here, okay? So therefore, I have a -1 here. Is that right? Okay. So therefore, this guy, right, is actually more correctly giving me 1 over -1/2 square root of minus x. Okay, so let me correct myself here. Because I look at this part, it doesn't conform to this part. So obviously, this serves as an inspection or check as well. Okay, so this will make sense already because you can see that this is x less than 0, right? So x is negative. So when I put in into this function, right, I will get positive x here, okay? Because I need this square root to be defined, okay, in order to have a line here, as you can see that. Okay, so therefore the negative here, right? So this guy is positive, this guy is negative. So therefore the overall f prime for x less than 0 is negative. Okay, that agrees with my line here, and that also agrees with my gradient here. Okay, so for this part, it's clearly positive. All right. Hey, hold on. Sorry. This is wait. So Pinghui. Okay, let me. Okay, so for x, where x is shouldn't it be minus square root x? Why is it minus square root x?
Theoretically, the negative value there shouldn't be any negative value within the square root, right?
Yeah, but you must understand that this x is negative.
Okay.
Yeah, so okay, so Pinghui, you're right to say that this square root cannot be negative, but because right, our x here is negative itself. So when we do the piecewise definition of the modulus function, this will always happen. Okay, so when x is negative, right, we throw a minus to the multiplication of this negative value to force it to be positive, because that's what the modular sign is doing. Okay, so it's like manually, it's like a bit manually making this modular sign work. All right, so therefore we have negative times negative. Is that right? Okay, so although this is a negative x, this whole thing is still positive. Okay, because this is defined for x less than 0. All right. Okay, good. So let's move on. So I think these 4 questions are quite straightforward. So I think I just do one, and maybe we can do question 3 together. Okay, because question 3, if you look at, let me see. Okay, hold on. I have a question from Lloyd. So you should identify the graph. Oh, no. This is just to demonstrate. Of course, from here, from the graph, technically, I am not able to know how this thing varies. Meaning to say, I do not know, just by looking at the graph without the function, I'm not able to really see how this actually looks like. That means the trend of the graph, right? I'm not able to tell, okay? Meaning to say, right, dependent on this profile, it could be like that, but it could be also maybe something like that, you know. Okay, because like that also satisfy this plus what? So which means that by virtue of estimating the gradient, right, it is difficult to exactly identify the trend of your f prime. Okay, so therefore, what I did here is I assume a function, right, that could possibly fit this graph here. Okay, and then I just try to draw the f prime, right, to show that the trend here would correspond to the differentiation of my function. Okay, so for this question, right, I just make this assumption so that I can, you know, relate the f prime and f more accurately. Is that right? Okay. So of course, if you are given such a question in your assessments, right, then of course I would be able to accept a wider variety of f prime, right, for your graph here. Okay, it wouldn't be exactly, it might not exactly be looking like that. Okay, although the positive, the polarity must agree. Okay, so as I mentioned, I just maybe want to go through one question of question 2 here. So it looks like maybe, I don't know, the rest, maybe question 30 looks the most interesting, just using quotient rule, in fact. Okay, so I'm just going to quickly run through question 30 here. So you can see that d of t is 1 plus 16t squared over 4t whole thing cube. Okay, 4t whole thing cube. So the first thing to do is maybe to expand out the term here, which is equivalent to 1 plus 16t squared. This one just leave it as it is. Then divide by, so cube must apply to 4. So therefore we have 16 times 4, which is 64, right? So hence we have 64t cube. Okay, so because we have not done the chain rule yet, so therefore we expand this 4t cube, right? Such that we have 4 cube times t cube. Okay, if you use the chain rule, then there's no need to do that. Okay, so once we have this, right? Of course, you can use the chain, you can use the quotient rule directly, or you can also simplify. Okay, you can also simplify. So therefore, let's use the quotient rule. So we have d prime t is equivalent to, so we have 64t cubed, then whole the denominator, differentiate the numerator, right? So we're going to get, differentiate 1 gets 0, so therefore differentiate 16t squared, get 32t. Then minus, so now we differentiate 64t cubed, so hence we get 64, so it has to be what, 18204, is it? No, 192. Okay, because it's 180, right? 180 plus 12, is that correct? Yeah, that looks correct. Huh? So therefore, this is 192t squared. So it's 192t squared, right? Then after that, hold your numerator. Okay, just tell me if I get this wrong. Huh? So therefore, over this thing square. Okay, so I'm just going to leave it as 64 whole thing square. Then multiply by t to the power of 6. Okay, because t3, you square the whole thing, right? You get t to the power of 6. Okay, so of course, this looks like a mess, and we can possibly simplify this. So therefore, it looks like we get 64 times 32 t power 4 minus 192 t square. And this is a minus 192 times 16 minus 192 times 16 t power 4. Okay, then this whole thing divided by this thing here. Okay, of course you can simplify, right? So I don't want to press any calculator, so therefore you can do the simplification on your own, right? So of course, in the process, right, the quotient rule is being employed. Questions on this Q30? Okay, good. So I think we just continue with this question 3. So question 3, you're supposed to find the equation of the tangent line and the normal line to the curve at the given point, which is actually 1, 1. So they give you in this form, which is y squared equals to x cubed. Okay, so Actually, such a question, you have two ways to solve for the gradient. So one is using implicit differentiation, which we are going to go through next week. But now, right, we can actually write this in a different manner. Okay, so therefore this is y squared equals to x cubed. So clearly we can rewrite y is equivalent to, so we just square root both sides, right? So when we square root both sides, we can actually have plus minus square root of x cubed. Okay, so y equals to plus minus square root of x cubed. So actually, you can split this up into two functions and then address each function separately. Okay, split this up into two functions and address each separately. So therefore, we have y equals to square root of x cubed, and the other guy is y equals to minus square root of x cubed. Okay, so we can actually work out each separately. And later on, of course, you will see that you actually have two tangent lines and two normal lines. Okay, so we're going to prove that in Desmos later on, but let me just show you how to go about getting the tangent line here. So naturally, we need the gradient, okay, because tangent line, normal line, it can be given by the point slope form of your equation. So hence, we have y prime. Okay, so y prime of x, right, is just equivalent to, so this is square root of x cubed. So for the square root of x cubed, right, of course, we can rewrite this as x to the power of 3 over 2. Okay, because it's x cubed, then to the power of half. So 3 times half, you get 3 over 2. So similarly, this guy will be minus x to the 3 over 2. Okay, so therefore, differentiating this, we have 3 over 2x. Then 3 over 2 minus 1, right, you're going to get half. Okay, so similarly, so the minus just throw one side, don't worry about that. So minus 3 over 2x to the power of half. Okay, so then once we have this, right, this is our y prime. So, but we want to know what is the gradient at 1, 1. So therefore, we can say at 1, 1, the gradient of the tangent. So let's call the gradient of the tangent mt. Okay, mt. So mt is equivalent to 3 over 2 times 1 to the power of half. So clearly this is just giving me 3 over 2. Okay, so a positive gradient here. Then at the same time, we can actually apply to the mt here. So this is mt. So there'll be 2 points whereby you have tangents. Okay, so mt is equivalent to minus 3 over 2. Okay, times 1, of course. So therefore, just minus 3 over 2. So at this juncture, right, maybe let's plot out y squared equals to x cubed. Okay, and see what happens. This is actually not a function, it's an equation. Okay, it's an equation. So let me show you. Okay. So if you look at this graph, right, it is actually not a function because it fails the vertical line test. Okay, and it is rightfully so because just now we have y equals to plus minus. Okay, so we have plus minus, right? It means that we have two values already. So at each particular x, you have two values. So it fails the definition of a function. All right. So hence, at 1, 1, so quite clearly, if I zoom into 1, 1 here, hold on. So if I zoom into 1, 1 here, you can inspect that at 1, 1, right? At 1, 1, there is actually this guy here. Okay, there's actually this guy. So what happens here is that you have a tangent here, but there's only one point that satisfy the graph here. So which means, right, although we got this is minus 3 over 2. This minus 3 over 2 is actually not satisfying 1, 1. Okay, so we can inspect. Because from this point, right, we can see that y at 1 is actually equivalent to what? It's actually equivalent to minus square root of 1 cube. So square root of 1 cube, right, is actually square root of 1. So it's actually minus 1. Okay, it's actually minus 1. So therefore, this graph, right, does not satisfy the point 1, 1. Okay, so therefore, this is actually not applicable. So let me just write. This is not applicable since this point, right, does not satisfy the coordinate 1, 1. Okay, so which means, right, at x equals to 1, this graph is actually giving me y equals to minus 1. Okay, so therefore it does not satisfy 1, 1 here. All right, so hence this is not applicable. Okay, this is actually at x equals to 1. Let me just correct this. All right, so hence we have just this point. Okay, just one point here, one tangent here. So once we have this, right, then actually we can write out what is our equation of the tangent really. Okay, so equation of tangent. So this is giving me y minus 1 equals to 3 over 2 x minus 1. Okay, so of course you can simplify. So hence the equation of the normal, right, will be just using the same point 1, 1. So therefore equation of the normal is just, or the gradient of the normal is just minus 1 over the gradient of the tangent. Okay, so gradient of the normal is just minus 1 over gradient of the tangent. So it's really just minus 2/3. So hence the equation of normal is just y minus 1 is equivalent to 3 minus 2/3 x minus 1. Okay, so you can work the equations out to put it in a proper form. Y equals to mx plus c. Questions? So of course in this process we just use direct differentiation without taking limits. Okay, looks fine. So this question 4 looks like an application question. So it says here that the car tires need to be inflated properly because overinflation or underinflation can cause premature tread wear. The data in the table show the tire life L in thousands of kilometers for a certain type of tire at various pressures P in kilopascals. Okay, so you're supposed to use a graphing calculator here, like Desmos, for example. So we're supposed to use the model to estimate the LDP when P is equals to 200 and P equals to 300. What's the meaning of the derivative? Okay, so of course we're not going to, key in all this in the calculator or something, right? But I just want to address the physical meaning of taking the derivative here. Okay, and then if you just do a visual inspection of the values here, we can actually somewhat sketch the graph. Okay, so let's have, let me see here. So it's actually P as a function of L, and my L actually varies from, wait, let me see. Oh, sorry, L is a function of P. So P varies from 179 to 311. So I'm going to assume that. So let's say that this is actually starting from 179. Okay, so let's say this is 179, and it goes all the way to 311. So hence this is my tire pressure P in kilopascals. And this guy is my life of my tire in thousands of kilometers. Okay, and then we have this is varying from 80. So lowest is about 80. So maybe I say that this part is about 80. And then it goes up. So it goes up and then goes back down to 95. So it looks like this guy, right, could, I don't know, possibly be something like that. So it's this point. And maybe I'm just, estimating this guy, yeah? So therefore I get possibly something that looks maybe like that. Okay? So this is about 95. Okay, let's say. So I have a few points here. Okay, something like that. So which means that there would be a maximum life at the so-called recommended tire pressure. Okay, so for those of you who maybe you have a family car or something, right? You might know that if you look at your so-called tire, so-called at the side of the tire, right? You will see that they actually gives you the recommended pressure. Okay, that is usually a range lah. Okay, a range of recommended pressure. So therefore, by just eyeballing this, right, we inspect that the ideal pressure appears to be at 242. Okay, 242. So therefore, maybe this is my maximum point. So therefore, okay, it may not be the absolute maximum, okay, because you have to see how you actually curve fit this. Okay, the way you curve fit this, right, actually may not the way you curve fit this may result in a point on the graph, on the line, right, that is higher than this point. Okay, that is actually higher than this point. So 242 may not be the absolute maximum, okay, if you try to curve fit this. All right, so hence, but nevertheless, this is about the maximum or close to the maximum, and this guy is actually at 242, and therefore this looks like this is 242, and therefore this value is about 130. Okay, so I'm just eyeballing this thing here. 130. Okay, so this could be my live pressure profile of my tire. Okay, so therefore, that's done for A. And let's look at part B. So it's supposed to use the model to estimate the LDP when P equals to 200 and P equals to 300. Okay, so of course, this is no big deal because since you are asked to estimate, right, you just have to find where is P equals to 200. So let's say this is 200 kilopascal. Okay, so this will be kilopascal. So then you just have to estimate what is the gradient here. Okay, it may not be exactly at a point, which is 200. You can see there's no 200 value here, so it's not exactly at a point. So therefore, you can actually find out what is the LDP here. Okay, then similarly, you can also repeat the same with P equals to 300. So maybe 3P equals to 300 is here. So therefore, I'll be able to estimate the DLDP here. So therefore, the DLDP is likely to be positive here and negative here. Okay, I roughly will know that and deduce that. The reason is because the maximum occurs at 242 kilopascal. Okay, this is my maximum. So in order to go to the maximum, right, 200 must have positive gradient. After 242, since this is the maximum, so it should drop. So therefore, the gradient will be negative here. Okay, so I hope we can all reconcile with that. So now, what is the meaning of this derivative? So therefore, the LDP here, the LDP is actually having the units of what? Of thousands kilometers. So 1,000, so let's put 1,000 kilometer per kilopascal. Okay, so of course everybody can somewhat deduce this unit easily because this is change in life. Change in life, right? It's actually change in thousands of kilometers. Okay, over the change in pressure, but change in pressure is also having the units of kilopascal. Okay, so this is the unit of the derivative. But how do we put this in layman terms? If I want to, ask you for a layman sentence on describing this, the LDP, how would you say it? Any takers? Any guesses? How would you explain the LDP, right, to a layman? Let's say for someone who is, having changed their tire and they want to know actually what does this the LDP mean pertaining to their tire life. Let's say you are the mechanic of the shop. How much distance it can travel per kilopascal? Almost there, almost there. And 50% correct. Any other taker? Almost there. Rate of wear with respect to pressure. Okay, we should this rate of wear with respect to pressure. First of all, the 1,000 kilometers is actually not the rate of wear. Okay, because rate of wear for tire usually is like, for example, right, I can define the rate of wear of a tire, right, by saying that, okay, how much of tread wear, okay, how much of tread wear per unit time, then that is known as the rate of wear. Okay, but this one is DL, so DL is actually, the life in thousands of kilometers, so it's actually not rate of wear. Okay, and furthermore, the second thing is that rate of wear with respect to pressure is quite technical also. Okay, so Nasini say how much distance it can travel as pressure change. How much distance it can travel? So that's quite similar to Ying Qian's guess. Okay, so good try. So let me just tell you how I would define it. Okay, so the LDP, right, actually means, so the LDP means the change of the tire life is change of the tire life. Okay, of course, in thousands kilometers, when, or rather for every 1 kilopascal increase in the pressure, in the tire pressure. Okay, so this is the representation. So it means, right, what is the change in the tire life in thousands of kilometers for every 1 kilometer, or sorry, 1 kilopascal increase in the tire pressure? Okay, because this is 1,000 kilometer per kilopascal. Okay, for every kilopascal, right? Okay, let's say this value. So I'm just going to say that, okay, let's say this value for this part. Let's say this part, let's say this part. Let's say this the LDP. So I know it's positive. Okay, so let me just assume that this guy, right, is equivalent to, okay, I'm just going to say that it is 30. Okay, this is of course approximately 30. Okay, let's say I estimate this to be 30, right? So 30,000 km per kilopascal. So what I can tell my client is this, okay? I say, hey, now you pump 200 kilopascal. I'll tell him that if you pump 1 kilopascal more, right, your tire can actually go for another 30,000 kilometers. You see that? Okay? So as a mechanic, right, let's say I know that the client only pumps at 200 kilopascal. So 200 kilopascal is actually not wrong, right? Of course, it's not ideal, but it's not wrong because maybe he wants his car, right, to feel softer, right? So when you have a lower tire pressure, right, actually your car actually feels softer, okay, and usually quieter. So therefore, it's more comfortable ride, not as so-called jumpy. So therefore, I can tell him, say, hey, now you pump 200 kilopascal, right, for your tires, right? Okay, so now, if you increase your tire pressure by 1 kilopascal, right, you can actually travel 30,000 kilometers more. Okay, that is the physical meaning, and that is what the client, right, can feel really. So, wow, I pump 1 kilopascal more, I can actually travel so much further more. You see the idea? Okay, so therefore, this is the concept, right, of the LDP here. Any question? So it's a change of tire life for every 1 kilopascal increase in pressure. Okay, so how would I tell the client who pumps 300 kilopascal? So because the client who pumps 200 kilopascal wants the ride to be comfortable. But I can tell you that the client who pumps 300 kilopascal, right, actually wants the car to be efficient. Okay, because I mean, logically, right, when you pump a tire pressure, when you pump your tire to a higher pressure, right, actually the tire becomes stiffer. So the contact between the tire and the ground actually reduces. Okay, so when that reduces, right, actually the tire is easier to roll. Okay, so I think you can somewhat reconcile that because as you know, right, like billiard balls, right, or ball bearings, they actually roll very easily. Okay, because they are very stiff, they're very hard. So their contact with the floor surface of the ground surface, right, is actually very small. So when you have very small contact, right, actually the resistance on the rolling, right, is lesser. So therefore, for a client who wants his car to actually be very fuel efficient, right, the client can pump a higher pressure. Okay, but when you do that, right, because the contact is less, so therefore the wear rate can be increased also, okay, between the tire and the ground because the contact is less, right? So the wear rate of the tire can be increased. So therefore the life is actually less. Okay, so for this client who pumps 300 kilopascal, right, I will tell him, hey, if you increase your tire pressure by 1 kilopascal, the life is going to decrease by a certain number of kilometers. Okay, so this is the DLDP, which is the negative value at this tire pressure of 300 kilopascal. Okay, you get that? Okay, so I hope you understand the LDP here and how we can actually use this value, right, to actually convince someone who doesn't know anything about derivatives, okay, to whether he or she should increase or decrease, right, his tire pressure. Okay, so therefore, next time when you buy a car, or if you have a car now, or you have a family car, right, you should, try to convince your friend or yourself, right, to have the so-called reasonable tire pressure within the recommended range. Okay, so that you maximize the life of the tire. Okay, of course, if you would like the more comfortable ride, you go towards the lower part of the range. Okay, if you want a more efficient ride or fuel efficient ride, you go to a higher part of the range. Okay, but maintain within that range, okay, of recommended pressure. Questions? Okay, if no, I think we have a good discussion on the worksheet questions today. Okay, so next lesson, I'm going to start with the week 9 material, okay, which is entirely on chain rule, right? So if no questions, thank you for your attention. Let's call it a day here.